You are on a ship. It's moving. You can't feel it. You look out the window and there is nothing. No planet, no moon, no station blinking in the distance. Just black. A black so complete and so permanent it stops feeling like a view and starts feeling like a wall. You've been out here for 6 years. You have 24 left to go. Most people, when they imagine a trip to the nearest star, picture something cinematic. A sleek ship, a dramatic launch, maybe some cryosleep, and then arrival. The alien world. The payoff. But here's the reality no one talks about. The journey to Proxima Centauri is not a movie. It is a multi-generational endurance test with no guarantee anyone survives to see the other side. Proxima Centauri is 4.24 light-years away. That sounds almost manageable until you do the math. Our fastest spacecraft, NASA's Parker Solar Probe, reaches about 430,000 miles per hour. At that speed, the trip to Proxima Centauri takes roughly 6,300 years. 6,300 years, and that probe isn't carrying humans. It isn't carrying food, water, air recyclers, or the psychological weight of knowing your great-great-great-grandchildren might die before the ship arrives. So here's the question nobody wants to answer. What would actually happen on that ship? Not in a movie. Not in a NASA press release. In reality. That's what I want to show you. Here's a number that puts this in scale. The entire recorded history of human civilization, from the first Sumerian city-states to right now, is roughly 6,000 years. We are talking about a voyage as long as all of recorded history. And under the most optimistic scenario, using a hypothetical propulsion system called a laser sail, the kind being developed by the Breakthrough Starshot Initiative, backed by Stephen Hawking and Yuri Milner. The fastest we could conceivably send a crewed vessel would travel at about 20% the speed of light. That gets the trip down to roughly 21 years. 21 years. A child born at launch is an adult when you arrive. Now we're in the realm of something almost thinkable, but only almost. Let's talk about what the physics actually does to a human body in deep space. In 2019, NASA published the results of the twin study, a landmark investigation comparing astronaut Scott Kelly, who spent 340 consecutive days on the International Space Station, to his identical twin Mark, who stayed on Earth. The findings were striking. Scott's telomeres, the protective caps on chromosomes that shorten as we age, temporarily lengthened in space, then shortened sharply upon return. His gut microbiome shifted. His gene expression changed in ways that persisted for months after landing. Roughly 7% of his genes did not return to their pre-flight baseline, and Scott Kelly was only gone for 11 months. On a 21-year journey, no one knows what happens next. We genuinely don't. Then there's radiation. Earth's magnetic field blocks most of the cosmic radiation that streams through the galaxy. Once you leave that bubble, past the moon, past Mars, past everything, you are exposed to galactic cosmic rays, high-energy particles moving at nearly the speed of light, punching through the hull of a spacecraft and through the cells of every person inside it. In 2020, researchers at University of California, Irvine exposed mice to simulated galactic cosmic ray conditions for 6 months. The results: significant memory impairment, anxiety-like behavior, and reduced ability to problem solve. The scientists called it, in the paper, cosmic ray dementia. We don't have a solution to this. A water wall thick enough to block cosmic rays would make the spacecraft too heavy to launch. Lead shielding works for some particles, not others. Right now, deep space radiation is the single biggest unsolved problem in human spaceflight, and for a 21-year voyage, it would be lethal in ways we can't fully model. Now let's put you back on that ship, not as a thought experiment, as a lived experience. You wake up. The lighting system simulates morning, a slow increase in warm light, because your circadian rhythm still runs on a 24-hour biological clock built over millions of years of evolution, and out here, there is no sunrise. You run for 30 minutes on a treadmill with bungee cords strapped across your chest to simulate gravitational load, because without resistance exercise, your muscles atrophy in microgravity within weeks, and your bones lose density at about 1% per month. Here's what most people don't understand. In the absence of gravity, the human body starts dismantling itself. It reads 0G as we no longer need structural support. Your spine elongates up to 3%, which sounds harmless until you realize it compresses nerve roots and causes chronic back pain that astronauts describe as excruciating. After exercise, you eat. The food is shelf-stable, freeze-dried, thermostabilized, irradiated. By year 3, Every crew member in every long-duration mission study reports the same thing: profound, gnawing food fatigue. The same textures, the same tastes, the same 200 options cycling on repeat. In a 2021 study by the Human Research Program, food satisfaction was listed as one of the top 3 threats to crew morale on long missions, alongside isolation and interpersonal conflict. And here's the part that gets me: you can't call anyone. At Proxima Centauri's distance, a signal traveling at the speed of light takes 4.24 years to reach Earth. You send a message. You wait 8.5 years for a reply. The people you launched with, your family, your friends, are living their entire lives in the gap between your words. Children you knew grow old. People die. And you find out with a 4-year delay. But here's where it gets interesting, because engineers and space psychologists are not waiting around. The most serious proposals for an interstellar mission don't just involve better engines. They involve rethinking what it means to be human on a ship. The concept under most serious discussion is the generation ship, a vessel large enough to sustain a self-replicating community. Not passengers completing a trip, but a civilization whose only purpose is the voyage itself. Children born on the ship would never know Earth. They would grow up, work, have their own children, and die, all before arrival. The ship is not transportation. It is a world. And that is a trap disguised as a solution. Because once you build a generation ship and launch it, the people inside it never chose to go. The first generation volunteers. Every generation after that is born into a mission they had no say in, on a ship they cannot leave, traveling toward a planet they will never see. Think about what that means. You need governance, because 1,000 people in an enclosed space over decades will fracture without structure. Governance means power, and power means politics. You need law, which means punishment. But where do you exile someone on a ship? You need reproduction policy, because population must remain stable. Too many people exhausts the air recyclers and the food system. Too few creates genetic bottlenecks that compromise the health of every future generation. In 2018, evolutionary biologist Cameron Smith at Portland State University modeled the minimum viable crew size for an interstellar voyage. His answer: 10,000 people. 10,000 to maintain enough genetic diversity to survive as a population across multiple generations. A crew of 150, the number most early proposals use, would experience measurable genetic inbreeding within 4 generations. 10,000 people, a small city, moving through the void. For 21 years at best, thousands at worst. We have been sending signals into space since 1974. We have not received a reply. One explanation, the one that keeps physicists up at night, is that interstellar travel is so catastrophically hard that any civilization capable of attempting it makes the attempt only once and fails. The Fermi paradox asks, if intelligent life is common in the universe, where is everyone? Maybe the answer is not that they never existed. Maybe the answer is that they launched, and the journey ended them. Proxima Centauri b, the planet orbiting our nearest stellar neighbor, sits in the habitable zone. It might have liquid water. It might, in some form we can barely imagine, have conditions hospitable to life. Scientists at the ESO confirmed its existence in 2016. The world is real. It is waiting. But the distance between us and it is not just space. It is bone, density, and radiation, and food fatigue, and the slow psychological unraveling of people who can never go home. We have spent all of human history learning to survive on one world. The next chapter asks whether we can survive the space between worlds, and whether we're willing to send people who never asked to go. The stars aren't waiting for us to be ready. They're just waiting.